So this video is about a topic that we didn't get to discuss in class, but it is on your homework. So I wanted to give you a little bit of background about it. It's called equivalent systems. So the idea in equivalent systems is that in some situations you might have a situation where you have quite a few forces and some couples, and the forces are going to cause some moments, and you really want to simplify the whole system as much as possible. But you want the simplification to give the same external effect that the more complicated system had before. So this is sort of an illustration of a system as it might be in real life, and then the equivalent system. So we have an I-beam, and it's being subjected to a couple different forces as well as a couple. And then the forces are also exerting a moment about the origin, which you see at the bottom of the picture. Now, the question is can I replace these several things, forces, couples, forces that are causing moments, with a much simpler representation that would have exactly the same effect on the I-beam? And when I say the same effect, we usually use the term external effect, which really means that the sum of the forces acting on the I-beam will still be the same, as well as the total moment that the I-beam is experiencing. It turns out that most often we can replace something that's more complicated like this by a system that consists of a force and a moment. And that, well, the moment we really should refer to as a couple. And those two together will give the same external effect as the more complicated system that we started with. So let's take a look at this in a more general way. So we're back to the blob. So we have this blob, and it's being subjected to two external forces, F1 and F2. There's also a moment that's acting on the blob. Now, if we look at it and we think about point O as a point that we want to take the moments about, we would notice that both F1 and F2 would create moments about point O. So not only do we have to think about what the external forces net effect is, but we also have to think about what kind of moment they're going to create. So when we find the equivalent system, which is consisting of a force and a moment, the equivalent force is the resultant force of F1 and F2, and the resulting moment about point O would be equal to the moment created by the two forces, F1 and F2, and the couple that existed in the original case. So again, what you're seeing is that we're simplifying this with a couple forces and a couple, shouldn't have used the word couple forces, but two forces and a couple, the two forces also producing moments, and we simplified it by two things, a resultant force and a couple. Here's a picture that shows sort of the intermediate steps of what's happening. So it's the same beginning piece, but then what we're looking at in this middle picture is we've moved the two forces to the origin. If you slide the vectors, you can, as long as they keep their orientation, you can move them. But when we move them to the origin, of course, as they're located at the origin, they don't actually create a moment about point O, but they did up here. And so you might notice that there's additional two moments added, or two couples added to this picture in the middle. One represents the moment that force 2 caused when it was at its original location, and the other one is the moment that force 1 caused. Now you can see that in that intermediate step we have two forces and we have three couples that could be added together. And when we add them all together, we get the resultant force. So this is sort of the intermediate step that we hadn't shown in the previous slide. The general idea of what we want to do is the things on the left-hand side are what we're after. when we have this system of forces and couples and we want to simplify it, we want to find a single resultant force which is just equal to the sum of the forces. So we just add them up like vectors. So keep in mind that that force equation right there is going to have an x and y component and perhaps even a z component depending on the scenario. And then our resultant couple, which will be about some point, will be equal to all the moments about that point that existed originally. So sort of making a comparison, this the sum of the moments about the origin right here would be equivalent to M1 and M2 added together, right? The M sub C was the couple moment that existed before, and so we have to add those as well. So to find the total momentum, the total couple that we're going to add to make our equivalent system, we have to add up all the couples that existed originally, plus all the moments about the origin or about whatever point they ask you to work with. You have to add those too, and then that gives us resultant. So you see that it's really just kind of like adding things up. And so I'm going to look at an example problem. So here is a case where they want us to find the equivalent resultant force and couple moment acting at A, and then the single force location measured from A. So what does that mean? So there's actually some instructions. It's really kind of thinking about doing this in a two-stage process. And in this problem, we're actually not going to need to add a moment, but we're going to put our resultant force at the right location so it causes the moment that we saw originally. Okay, so the idea is the first thing that we have to do is we have to find the net force in each direction. That means we're going to look at the sum of the forces in the x direction and the sum of the forces in the y direction. And that's just looking at what's going on in this picture here. And so that's going to tell us what our total force is for our equivalent system. Then, in this particular problem, we don't have any couples acting on that beam, but we're going to see what kind of moment about point A do my three forces create, because my resultant moment at the end has to be the same. And so now in steps 1 and 2, we have figured out what the total moment that we need for our equivalent system and our total force. But this one is going to be a little bit different, and this is the kind of problem that you're going to see, I think, on your homework, is instead of just saying, okay, we have this force, the resultant force that we found, and we're also going to say that there's this couple that's exerted on the beam. What we can do is we can put the force at the correct location so that it causes the resulting moment that we had calculated in step 2. All right, so let's see, once we do it, how that works together. So I wanted to get a little bit more room to work in. So we're going to look at the forces in the x direction. And so what do we have? We have the 100-pound force, and we want to look at its x component using our triangle. That will be given by 3 over 5. And then the 50-pound force has an x component. And oops, I went into the picture, sorry about that. And because of the way the angle is defined, it's using the sine of 30 to find the x component. And so those two together give me a net force in the x direction of 85 pounds. Now let's look at the forces in the y direction. We have 200 minus 100 times 4/5, and then plus 50 times the cosine of 30 degrees. And so those are all the y components of the forces that we see acting on the beam, and they're going to add up to be 163.3 pounds. Now the total force, this is the resultant force, is going to be the square root of fx plus fy, those two squared, take the square root. That ends up to be 184 pounds. The angle that that's going to be at ends up to be 62.5 degrees. So the idea is that our force, our resultant force for these three, Fr, is equal to 184 pounds at 62.5 degrees. So it would be like up and to the right. All right, so we know that, but what is the moment? All three of those forces are displaced from point A, so they're also going to produce a moment about point A. And so I can't just replace those three forces by a single force without thinking about the moment that they are going to produce. So let's figure out what the moment about point A is. So we just start at point A, and I'm going to go out along the beam, and as I hit a force, I'm going to calculate the moment that it would produce. The 200-pound force is it's 3 feet. It's 3 feet away from the from point A, and it's going to produce a counterclockwise rotation, so I'm making that positive. Next, I get to the 100-pound force. Only the y component is going to produce a moment about point A, only the piece that points down, and that's going to cause a clockwise rotation, so that's going to be minus 100, and the y component is going to be given by 4/5 of that, and it actually is 6 feet away. And then finally we get to the 50-pound force. Again, only the y component will produce a moment, and that's actually going to be a positive moment. And the distance for that one is 9. So if I add all these together, I get 509.7 pounds times feet. And it is positive, so that is counterclockwise. And so what I want is I want to figure out where to put the force. So like what distance away from A can I put this force so that it produces this moment? And so my question is reduced to, I'm going to take Fr times some distance is going to give me my m sub A. Now, it's important when we think about this, do I want to use 184 pounds? Because that is a force that's at an angle. And the answer is no. I should be using the y component of that force because only the y component is going to produce the moment. The x component doesn't contribute. And so figuring out what D is going to be done by calculating the ratio of the moment I found right here, which is 509.7, over the y component of the force, which was 163.3. And so that ends up to be 3.12 feet. And so what this actually means is that if I took this force and I placed it at this location, it would give the exact same effect as the three forces that we see. So like if I kind of put it like right there, and then the distance from here to here would have been 3.12 feet. And I actually could have replaced the three forces by a single force in this scenario. I actually didn't need to add a moment. And that's just an example of how we find an equivalent system.